The winter wind possessed a different kind of bite in the Black Hills, a lesson John Harris learned harshly in 1885. Despite feeding cord after cord of pine into his stone fireplace, his cabin's temperature plummeted to near freezing, just 3 feet away. He had meticulously constructed his cabin according to the accepted wisdom of Dakota Territory settlers, tight log walls and a sturdy stone chimney rising through the roof, a design considered both standard and reliable. Yet, by spring, he had burned an exorbitant amount of wood, far more than any 2 men should require, and still endured shivering nights. Across the territory, homesteaders were facing the same disheartening reality, their cabins built by the book failing to provide adequate warmth as the seasons turned. The building inspector scoffed at Harris's unconventional idea of burying his chimney underground, warning that such a modification would invalidate his insurance. Undeterred, over the next 2 years, Harris quietly implemented an ingenious technique, blending the time-honored wisdom of Swedish farmhouses with insights gleaned from a Lakota builder. When the brutal freeze of 1887 descended, plunging neighboring cabins to a frigid 10 degrees Fahrenheit, Harris maintained a comfortable 61 degrees Fahrenheit, using only half the wood. What secret understanding of heat did he possess that eluded every other frontier builder? Harris had strategically chosen his homestead site in a natural clearing located 8 miles northwest of Deadwood. The land gently sloped towards Whitewood Creek, providing convenient access to both fresh water and the dense stands of ponderosa pine that blanketed the surrounding ridges. Situated near 4,000 feet in elevation, the area experienced regular sub-zero winter temperatures, yet remained suitable for farming. Swedish immigrants like Harris possessed an innate understanding of timber, and the Black Hills appeared to offer a boundless supply of straight-grain logs, ideal for cabin construction. The prevailing frontier building method, honed through decades of trial and error across the American West, was meticulously documented in Army engineering manuals and settler guides disseminated by territorial governments. A vertical chimney, constructed of stone or brick and extending through the roof peak, was considered essential for generating a strong draft, efficiently drawing smoke from a large open hearth or a centrally positioned cast iron stove. The logic was seemingly irrefutable. Hot air rises, creating natural convection that pulls combustion gases upward and out of the dwelling. Taller chimneys equated to stronger draft, cleaner burns, and reduced smoke backing into the room. Local masons typically charged $12 for a standard fieldstone chimney, and most settlers possessed the skills to complete the work themselves using readily available materials. Military engineers had rigorously tested this design at frontier posts spanning from Montana to Texas, deeming it reliable across diverse climates and fuel types. The system utilized easily accessible materials, required only basic masonry knowledge, and could be rapidly constructed by homesteaders working alone or with minimal assistance. Territorial building codes explicitly endorsed vertical chimney construction, and insurance companies offered standard rates for cabins adhering to these specifications. Every hardware supplier in the region stocked the necessary mortar, flue pipes, and dampers for conventional installation. However, Harris discovered fundamental flaws that the manuals overlooked. His chimney drew so forcefully that he could feel icy air rushing across the floor toward the fireplace, creating a circular airflow pattern that whisked warm air directly up the flue before it could effectively heat the living space. On calm nights, interior temperatures fluctuated dramatically, varying by as much as 15 to 20 degrees Fahrenheit between floor level and ceiling height, with the warmest air pooling uselessly near the roof logs. When prairie winds battered the cabin, downdrafts occasionally forced smoke back into the room, compelling him to constantly adjust dampers or risk suffocating on the fumes. The stone chimney itself acted as a massive heat sink, relentlessly absorbing warmth from the fire and conducting it directly to the exterior through 18 feet of exposed masonry. Harris calculated that nearly half the heat generated by his fire was being squandered through the chimney structure and the powerful draft it created. Snow melted in a perfect circle around the chimney's base, revealing the leakage of waste heat through the foundation, while his water bucket froze solid just 10 feet away. Neighbors recounted identical problems, some burning through as much as 5 cords of pine in a single winter and still struggling to maintain comfortable temperatures. Harris drew upon knowledge from his childhood in Smaland province, where winter temperatures rivaled the harshest conditions the Black Hills could offer. Swedish farmhouses had employed radically different heating approaches for centuries, including stone flue systems designed to capture and store heat rather than immediately venting it to the outside. His father had built their family home with a masonry stove incorporating internal channels, allowing hot gases to warm the stonework before exiting through a relatively small exterior flue. The underlying principle was heat retention, not rapid evacuation. During his second winter in the territory, Harris encountered a Lakota builder working on structures near the burgeoning settlement. The man explained how traditional winter lodges were ingeniously designed to harmonize with the earth, leveraging the ground's natural thermal mass to store and gradually release heat throughout the long winter nights. Lodge fires were strategically built to warm the earth floor, which then radiated heat upward for hours after the flames died down, long after the fire itself had subsided. This concept challenged everything Harris had previously learned about frontier construction. Yet the thermal efficiency was undeniable. When Harris began discussing alternative heating methods with neighbors and local suppliers, he encountered swift and unwavering resistance. Established builders dismissed any deviation from proven methods as reckless risk-taking that could endanger families and property. The territorial building inspector, Alan Morrison, explicitly warned that modifications to the standard chimney design might invalidate insurance coverage and building permits. Local hardware merchants voiced skepticism about special orders for materials required to construct underground flue systems, questioning their reliability and availability. Longtime residents pointed to the numerous successful cabins built according to standard specifications, arguing that high fuel consumption was simply the price of frontier living. They dismissed Harris's concerns about heat loss as the complaints of a newcomer unwilling to accept the realities of Dakota Territory winters. Several neighbors suggested that his problems stemmed from poor construction technique rather than inherent flaws in the design, implying that proper masonry work would resolve his heating difficulties. Morrison inspected Harris's cabin twice during his second winter, finding no violations of territorial building codes, but warning that any significant modifications would require approval from the Territorial Engineering Office in Bismarck. The process could take months and might ultimately require him to rebuild the entire heating system according to standard specifications. Morrison emphasized that experimental approaches lacked a proven track record of safety or reliability, while the conventional method had been tested across thousands of frontier installations. By the spring of 1886, Harris was convinced that the conventional chimney system wasted a significant portion of its heat through rapid venting and inadequate thermal storage, but he only possessed fragments of a viable solution. He knew that Swedish farmhouses utilized internal flue paths to capture waste heat, and he had learned that indigenous building methods prioritized storing heat in thermal mass rather than immediately venting it. However, he had yet to determine how to effectively combine these principles into a practical system suitable for log cabin construction in the unique conditions of Dakota Territory. The ultimate challenge was integration, how to capture the waste heat from combustion, store it effectively in readily available materials, and release it gradually to maintain consistent interior temperatures throughout long winter nights. Harris recognized that solving this problem would necessitate abandoning conventional wisdom and developing an entirely new approach to frontier heating. The solution began with the earth itself. In late September of 1886, Harris commenced his excavation, taking advantage of the dry autumn weeks before the ground froze to dig a trench beneath his cabin floor. The excavation measured 30 feet in length, running east to west parallel to the cabin's main wall, positioned 8 inches beneath the existing floorboards, and extending from directly under his cast-iron stove to a point 15 feet beyond the cabin's exterior wall. The trench itself was 8 inches deep and 10 inches wide, sized to accommodate the clay drainage pipe he had ordered from a supplier in Rapid City. Swedish farmhouse construction had instilled in Harris the principle of lateral heat distribution through buried channels. His grandfather's stone house in Smaland had featured a network of flue passages that ran beneath the main floor before connecting to an exterior chimney, allowing combustion gases to transfer heat to the surrounding masonry and earth before exiting. The system required precise engineering to maintain proper draft while maximizing heat extraction, carefully balancing the competing demands of smoke evacuation and thermal retention. The Lakota builder, who introduced himself as Joseph Red Bear, returned to Harris's homestead in early October to demonstrate ground-coupled heating principles. Red Bear showed Harris how traditional winter lodges utilized fire pits positioned to warm the packed earth floor, which then radiated heat upward through buffalo hides and other coverings throughout the night. The earth beneath the fire pit absorbed thermal energy during active burning periods, then slowly released that stored heat for hours after the flames died down. The principle was thermal storage, not immediate heat distribution. Red Bear helped Harris understand the critical relationship between soil density, moisture content, and heat retention capacity. Dense, slightly moist clay held heat longer than loose, dry sand or rocky soil. The Black Hills clay found 8 inches beneath Harris's cabin provided ideal thermal mass properties, capable of absorbing significant heat energy and releasing it gradually over extended periods. This natural heat sink could effectively capture waste heat that would otherwise escape up a conventional chimney. Harris installed 8-inch diameter clay drainage pipes, specially ordered for their heat resistance and durability in underground applications. The pipe sections were joined with mortared connections, creating an airtight channel that would direct hot combustion gases horizontally through the earth before allowing them to exit. The installation required precise grading, with the pipe sloped upward at 1 inch per 30 feet of horizontal run to ensure proper draft while maximizing ground contact time for heat transfer. The excavation revealed additional challenges. Groundwater seepage necessitated lining portions of the trench with fieldstones and installing drainage channels to prevent water accumulation around the pipe. Root systems from nearby pines had to be carefully cut and sealed to prevent future growth that might damage or block the flue. The clay pipe needed protection from frost heave, requiring Harris to backfill with sand and gravel that would allow thermal expansion without cracking the connections. Construction of the underground system took Harris nearly 3 weeks of steady work, complicated by the need to maintain structural support for his cabin floor while excavating beneath it. He used temporary wooden bracing to support floor joists during the digging process, then carefully backfilled around the installed pipe to restore foundation stability. The final connections required modification of his existing stove installation, adding a high damper system that could direct exhaust gases either through the underground channel or up a shortened vertical chimney. Red Bear contributed invaluable knowledge of earth thermodynamics that proved essential to the system's success. He explained how different soil types conducted and stored heat at varying rates, helping Harris position the underground flue for maximum ground contact with a clay layer that provided optimal thermal mass. Red Bear also demonstrated techniques for testing soil temperature at depth, showing Harris how to monitor the ground heat storage process and adjust burning patterns to maximize efficiency. The completed installation included a cleanout access point positioned halfway along the underground flue length, accessible through a small trap door cut into the cabin floor. This service port allowed Harris to remove accumulated creosote and debris that could reduce system efficiency or create fire hazards. The design borrowed from canal construction techniques, where long underground passages required periodic maintenance access to remain functional. Field testing began immediately with the first cold snap of November 1886. Harris burned 3 cords of split pine in his modified stove system, meticulously recording fuel consumption, interior temperatures, and system performance. The underground flue channeled hot exhaust gases through 30 feet of earth before allowing them to exit through a reduced-height exterior chimney, capturing waste heat that would have been immediately lost in a conventional installation. Temperature measurements revealed dramatic improvements in heating efficiency. Harris's cabin maintained interior air temperatures of 56 degrees Fahrenheit when outside temperatures plummeted to -12 degrees Fahrenheit, while neighboring cabins using standard vertical chimney systems struggled to maintain 28 degrees Fahrenheit under identical conditions. Floor surface temperatures showed even greater differences, with Harris's cabin averaging 46 degrees Fahrenheit at floor level compared to 28 degrees Fahrenheit in conventional cabins. The underground thermal storage effect became apparent during extended cold periods. After burning wood for several hours, Harris's cabin continued to receive radiant heat from the warmed earth beneath the floor throughout the night, maintaining relatively stable temperatures, even when the fire died down to coals. Neighboring cabins experienced rapid heat loss once active burning decreased, requiring more frequent stoking and higher fuel consumption to maintain livable conditions. Fuel efficiency testing confirmed the system's effectiveness. Harris reduced his winter wood consumption from 3 cords to 2 cords while achieving significantly higher interior temperatures than conventional heating methods. The underground flue captured approximately 60% of the waste heat that would have been immediately vented through a standard chimney, redirecting the thermal energy into ground storage and gradual release through the cabin floor. By the spring of 1887, Harris had documented clear evidence that horizontal underground flue systems could dramatically outperform conventional vertical chimney installations in frontier heating applications. The combination of Swedish thermal storage principles and Lakota ground-coupled heating techniques had produced a working system that challenged fundamental assumptions about frontier construction methods. The success of the underground flue revealed new problems Harris had not anticipated. While his cabin maintained higher average temperatures than conventional builds, interior conditions fluctuated wildly throughout each 24-hour cycle. Morning temperatures might reach 62 degrees Fahrenheit near the stove, then drop to 45 degrees Fahrenheit by dawn despite continuous burning. The log walls themselves absorb heat during the day, but released it rapidly to the exterior, creating a thermal roller coaster that wasted fuel and compromised comfort. Wall surface temperatures told the story. Harris measured his interior log walls at dawn and found them averaging 34 degrees Fahrenheit when outside temperatures hit minus 15 degrees Fahrenheit. The bare wood offered minimal thermal storage, absorbing heat from room air during peak burning periods, then conducting that warmth directly through the logs to the exterior. The walls functioned as thermal bridges, channeling interior heat outside rather than storing and gradually releasing it back to the living space. Friedrich Keller, a German-trained carpenter and plasterer working homestead construction throughout the Black Hills, brought old-world knowledge of interior wall treatments. Keller had learned his trade in Bavaria, where stone and timber houses required interior finishes that could moderate temperature swings and improve heating efficiency. Traditional German construction used thick clay plasters applied over wooden lath systems, creating thermal mass that absorbed and slowly released heat rather than conducting it directly to the exterior. Keller initially dismissed Harris's concerns about thermal storage, arguing that properly chinked log walls provided adequate insulation for frontier conditions. Most German immigrants in the territory built conventional log cabins without interior wall treatments, accepting temperature fluctuations as inevitable in wooden construction. Keller had installed standard mud chinking and basic interior finishes in dozens of area cabins, following practices that worked adequately with conventional heating systems. But Harris's underground flue created new demands for interior thermal performance. The captured ground heat provided steady warmth that needed to be absorbed, stored, and redistributed rather than immediately lost through the walls. Harris convinced Keller to experiment with interior wall mass as a complement to the underground heating system. Combining German plastering techniques with the thermal storage principles that made the buried flue effective, the wall treatment required extensive preparation. Keller split local aspen saplings into thin lath strips, each measuring 1/4 inch thick by 1 inch wide, then nailed these strips horizontally across the interior log surfaces at 4-inch intervals. The lath provided attachment points for the clay plaster while creating air gaps that improved insulation performance. Installation required careful attention to log settlement since green timber continued to shrink and shift for months after construction. Keller mixed his plaster using local clay, sand, chopped straw, and lime obtained from a kiln operation near Rapid City. The mixture combined 1 part clay with 2 parts sand and sufficient chopped straw to prevent cracking during the drying process. Lime addition improved durability and reduced shrinkage, creating a hard surface that would maintain structural integrity through repeated freeze-thaw cycles. The final plaster thickness measured 1 inch across all interior wall surfaces. Application required multiple coats applied over several weeks. Keller first applied a rough base coat that filled gaps between lath strips and created uniform surface texture. A second coat smoothed irregularities and built the plaster to full thickness, while a final finish coat provided smooth surfaces suitable for frontier living conditions. Each coat needed to dry completely before application of the next layer, extending the process through most of November 1887. Red Bear contributed additional thermal mass concepts, focusing on floor systems. He explained how traditional lodge construction used stone and earth floors that absorb heat from fires and radiated warmth upward throughout the night. The principle was thermal battery storage, with dense materials like stone providing much greater heat capacity than wood or earth alone. Red Bear suggested incorporating stone elements into Harris's floor system above the underground flue location. Harris obtained flagstone slabs from a quarry near Spearfish, selecting pieces that measured 2 inches thick and roughly 2 feet square. The stones came from local limestone formations that offered good thermal mass properties while remaining workable with frontier tools and techniques. Transportation required multiple wagon trips, with each load carrying approximately 1 ton of finished stone suitable for interior floor installation. Installation of the stone floor proved more complex than anticipated. Harris needed to reinforce floor joists beneath the flagstone areas to support the additional weight, adding extra timber supports and cross-bracing. The stones required careful fitting and leveling, with gaps filled using mortar mixed from sand, lime, and local clay. The finished stone floor covered approximately 60% of the cabin's living area, positioned directly above the underground flue path, where thermal transfer would be most effective. The combination of interior wall plaster and stone floor created a thermal storage system that worked in concert with the underground flue. Hot exhaust gases warmed the earth beneath the stone floor, which absorbed and stored that heat throughout the burning cycle. The stone then radiated warmth upward into the room, while the plastered walls absorbed excess heat from the room air, storing it during peak temperatures and releasing it gradually as air temperatures declined. Temperature measurements confirmed dramatic improvements in thermal performance. Interior wall surfaces now averaged 57 degrees Fahrenheit at dawn when outside temperatures reached -8 degrees Fahrenheit, compared to 34 degrees Fahrenheit for bare log walls in neighboring cabins. The flagstone floor surface measured 61 degrees Fahrenheit under identical conditions, providing consistent radiant heat that eliminated the cold feet problems common in conventional cabin construction. The thermal mass system reduced temperature swings from 20 degrees variations to just 5 degrees throughout the daily heating cycle. Interior air temperatures remained within a narrow band between 52 degrees Fahrenheit and 57 degrees Fahrenheit overnight, compared to swings from 30 degrees Fahrenheit to 50 degrees Fahrenheit in cabins without thermal storage. The stable temperatures improved comfort while reducing fuel consumption since the stove no longer needed to compensate for rapid heat loss during low burning periods. Keller documented the installation process and results, noting that the combined wall and floor thermal mass created interior conditions unlike anything he had experienced in conventional frontier construction. The system transformed Harris's cabin from a typical log dwelling with extreme temperature variations into a structure that maintained consistent, comfortable conditions with minimal fuel input. The integration of German wall techniques with indigenous thermal principles had produced a frontier building system that challenged assumptions about what was possible with available materials and methods. By winter's end, Harris had proven that thermal mass could be successfully integrated with underground heating systems to create superior interior conditions. The combination of captured waste heat and interior thermal storage provided a foundation for further improvements to frontier heating efficiency. However, spring weather exposed fatal flaws in Harris's heating system that had remained hidden during the steady cold of winter months. As outside temperatures began fluctuating between freezing nights and warming days in March of 1888, the underground flue system created new problems that threatened to negate its winter advantages. Condensation began forming inside the buried clay pipe as warm spring air met cool underground surfaces, creating moisture that dripped back toward the stove and mixed with ash residue to form thick tar-like creosote deposits. The condensation problem stemmed from temperature differentials that did not exist during consistent winter cold. Spring days warmed the exterior chimney exit and the above-ground portions of the flue system, while the buried pipe sections remained cold due to months of ground contact. When Harris burned wood during cool spring mornings, hot exhaust gases cooled rapidly as they traveled through the underground section, causing water vapor to condense out of the smoke stream and accumulate in the lowest points of the horizontal pipe run. Patrick O'Leary, an Irish stonemason who had worked canal tunnel construction in Pennsylvania before migrating to the Black Hills, brought expertise in managing long underground passages that Harris desperately needed. O'Leary had supervised the installation of ventilation systems in canal tunnels that extended for miles beneath rivers and hillsides, dealing with condensation, drainage, and access problems identical to those plaguing Harris's heating system. Canal work had taught O'Leary that any long underground passage required service access points and drainage systems to remain functional over time. O'Leary initially dismissed Harris's underground heating concept as impractical, arguing that a horizontal flue violated fundamental principles of draft and combustion safety. His experience with tunnel ventilation had shown him the difficulties of maintaining airflow through long horizontal passages, especially when those passages accumulated moisture and debris. O'Leary believed that vertical chimneys provided the only reliable method for removing combustion products from residential heating systems. But examination of Harris's clogged flue system revealed problems that O'Leary recognized from canal construction. Creosote and condensation had accumulated at the lowest point of the underground pipe run, exactly where gravity would deposit any liquid that formed inside the system. O'Leary had seen identical accumulations in canal ventilation shafts where temperature changes and moisture created deposits that gradually reduced airflow and created safety hazards. O'Leary designed a service access system that borrowed directly from canal tunnel engineering. He installed a clean-out port at the midpoint of the underground flue run, accessible through a cast-iron door set flush with the cabin floor. The access port measured 8 inches square, large enough to allow the removal of accumulated debris, while small enough to maintain the structural integrity of the floor system. A removable grate inside the access port prevented large objects from falling into the flue while allowing easy access for cleaning tools. The cleaning process required specialized tools that O'Leary adapted from canal maintenance equipment. He fashioned a flexible rod system using joint sections of iron wire tipped with a scraping blade that could remove creosote deposits from the interior walls of the clay pipe. The rod sections could be assembled to reach the full 30-foot length of the underground flue, allowing thorough cleaning from the single access point without requiring excavation of the entire system. Red Bear contributed seasonal management concepts that addressed the overheating problems Harris experienced during spring warm spells. Traditional lodge heating systems included methods for controlling heat output and airflow based on changing weather conditions. Recognizing that heating needs vary dramatically between deep winter cold and shoulder season temperature swings, Red Bear explained how lodge builders created adjustable ventilation systems that could be modified as conditions changed throughout the heating season. The solution required the installation of a bypass damper system that could redirect exhaust gases based on seasonal heating demands. Harris installed a cast-iron damper valve immediately downstream. From his stove, a lever accessible from the main living area provided complete control. During the depths of winter, the damper system directed all exhaust gases through an underground flue network. This maximized heat capture and effectively turned the ground into a vast thermal storage unit. In the milder shoulder seasons, the damper could redirect the exhaust directly to a shortened vertical chimney, bypassing the underground system altogether. This bypass chimney required meticulous engineering to ensure proper draft even when the underground system was offline. To accomplish this, Harris incorporated a secondary flue pipe that connected to the main exhaust stream before the damper valve. This pipe ran directly through the cabin roof, utilizing an 8-inch diameter opening. The bypass system also had its own damper controls, giving Harris the ability to precisely adjust airflow between the underground thermal storage and the direct exhaust, depending on the specific heating demands. Seasonal operation demanded that Harris develop tailored burning and maintenance schedules that align the system configuration with the ever-changing weather conditions. Throughout sustained cold periods, he operated in full underground mode, capturing every bit of waste heat and storing it within the Earth's thermal mass. As spring arrived and temperatures began to fluctuate above freezing during the day, Harris switched to bypass mode for daytime burning. This prevented the cabin from overheating while still maintaining the underground heat storage for the colder nighttime hours. This dual-mode system effectively eliminated the condensation problems that had plagued spring operation of the original underground flue. By bypassing the buried pipe sections during warmer weather, Harris prevented the temperature differentials that caused moisture to condense within the system. The underground flue remained dry and clear, ready for immediate use when cold weather returned, without requiring extensive cleaning or maintenance. Regular maintenance became essential for long-term system performance. Harris cleaned the underground flue twice each year, once in late spring after switching to bypass mode, and again in early fall before resuming full underground operation. Each cleaning session removed roughly a half pint of creosote and condensed moisture, preventing accumulations that could reduce system efficiency or even create fire hazards. Performance testing confirmed that these seasonal control systems maintained heating efficiency while preventing common operational problems. During the spring of 1888, Harris's cabin maintained interior temperatures of 58 degrees Fahrenheit during overnight periods when outside temperatures plummeted to 28 degrees, relying solely on the underground thermal storage system during these hours. Daytime heating utilized the bypass system, preventing interior temperatures from exceeding a comfortable 65 degrees, even when outside conditions warmed into the 40s. Despite the operational complexity of the dual-mode system, fuel consumption remained remarkably stable at just 2 cords per heating season. The ability to precisely match system configuration to heating demands prevented both underheating during frigid periods and overheating during milder weather, ensuring optimal fuel efficiency across varying seasonal conditions. Harris had effectively solved the fundamental problem of seasonal heating control, a challenge that plagued both conventional and experimental heating systems of the time. By the autumn of 1888, Harris had perfected a complete heating system that combined underground heat capture, thermal mass storage, and sophisticated seasonal operational control. The seamless integration of Irish engineering principles with indigenous thermal management concepts had resulted in a truly unique frontier heating system, one capable of maintaining optimal performance across the full spectrum of Black Hills weather conditions. The winter of 1887 to 1888 brought weather so extreme that it pushed every heating system in the Black Hills to its absolute breaking point. A persistent high-pressure ridge stalled over the northern Rocky Mountains in late December, creating what meteorologists would later recognize as one of the most severe Arctic outbreaks in territorial records. Temperatures plummeted to minus 25 degrees Fahrenheit and remained below minus 15 degrees for 7 consecutive days, accompanied by winds that drove effective temperatures to a bone-chilling minus 40 degrees across exposed areas. Conventional heating systems failed catastrophically under this sustained extreme cold. Neighboring cabins with standard vertical chimney designs experienced interior temperatures that plummeted to a frigid 8 degrees Fahrenheit, despite continuous burning. The Thompson family, residing half a mile southeast of Harris in a cabin built according to standard territorial specifications, recorded interior air temperatures of a mere 6 degrees at floor level on the third night of the deep freeze. Their consumption of split pine reached nearly 1 cord per day as they desperately struggled to maintain any interior warmth above freezing levels. Chimney systems became outright structural hazards as the extreme conditions exposed fundamental design flaws. The Morrison cabin suffered a chimney fire when accumulated creosote ignited during desperate attempts to increase heat output, forcing the family to evacuate in minus 20 degrees conditions while flames damaged roof timbers and threatened total structural loss. The Palmer homestead experienced complete chimney blockage when rapid temperature changes cracked the stone flue, forcing smoke back into the living space and rendering the cabin uninhabitable until repairs could be completed. Emergency measures adopted by conventional cabin owners only serve to highlight the inadequacy of standard frontier heating methods. The Hendrickson family moved their entire household into a single room and hung blankets across doorways in a futile attempt to concentrate what little heat their fireplace could provide. 3 neighboring families abandoned their cabins altogether, seeking shelter in Deadwood until the extreme weather passed. Local hardware stores were completely cleaned out of emergency heating supplies as desperate homesteaders purchased every available oil lamp, candle, and portable heating device to supplement their failing primary systems. In stark contrast, Harris's integrated heating system performed flawlessly, without any need for modification or emergency measures, throughout the entire extreme weather event. Interior air temperature measurements remained stable at a comfortable 61 degrees Fahrenheit, even when outside conditions reached a brutal minus 25 degrees. The flagstone floor surface recorded consistent temperatures of 58 degrees, providing radiant warmth that prevented the frozen floor conditions experienced in neighboring cabins. His fuel consumption did increase, but only to approximately 3 cords for the week-long cold snap, still substantially less than the 4 to 5 cords burned by conventional systems that achieved far inferior results. The thermal mass components of Harris's system proved absolutely critical during the extended extreme conditions. His plaster walls maintained interior surface temperatures of 55 degrees throughout the crisis, preventing the interior frost formation that plagued bare log construction in neighboring cabins. The underground flue system continued operating at full efficiency, capturing waste heat that conventional chimneys simply vented directly to the exterior. This combination of heat capture, thermal storage, and controlled release maintained livable conditions without requiring emergency modifications or dangerous burning practices. Word of Harris's heating success spread rapidly through the scattered homestead community as neighbors witnessed the dramatic performance differences during the crisis. Territorial Building Inspector Alan Morrison paid an unofficial visit to Harris's cabin on the 4th day of the deep freeze, recording interior temperature readings and documenting system performance for his quarterly report to Territorial Headquarters. Morrison noted that Harris's cabin remained warm enough for normal daily activities, while neighboring structures had become barely habitable despite maximum heating efforts. Local supply merchants began receiving inquiries about materials needed to construct underground flue systems. Gustav Henley, who operated the main hardware supply in Deadwood, reported increased demand for clay drainage pipe, flagstone, and specialized masonry supplies during the weeks following the extreme weather event. Henley contacted suppliers in Rapid City and Cheyenne to investigate the availability of materials needed for underground heating installations, responding to direct requests from homesteaders who had personally witnessed Harris's system performance. Regional homesteading associations took formal notice of Harris's heating innovations following the 1887 to 1888 winter demonstration. Mary Roberts, secretary of the Montana-Dakota Homestead Association, visited Harris's installation in the spring of 1888 to document construction details and performance data for inclusion in association building bulletins. Roberts meticulously measured and recorded specifications for the underground flue system, thermal mass installations, and seasonal control mechanisms, preparing detailed technical descriptions for distribution to homesteading families throughout the Northern Plains. The association's bulletin, published in September of 1888, marked the first official recognition of underground heating systems as a viable alternative to conventional frontier construction. Roberts included detailed construction specifications, material lists, and performance comparisons based on Harris's documented results during the extreme weather testing. The bulletin reached homesteading families across Montana, Dakota Territory, Wyoming, and Colorado, spreading knowledge of underground heating principles far beyond the immediate Black Hills region. Technical validation came from unexpected sources as word of Harris's system reached professional engineering circles. Railroad engineers working on Northern Pacific construction through the Rockies encountered similar heating challenges in construction camps and maintenance facilities. Company engineers investigated Harris's underground flue principles for application in railroad buildings, recognizing the potential for significant fuel savings and improved working conditions in remote mountain facilities, where heating costs represented a substantial operational expense. Construction of derivative systems began appearing across the northern frontier as Harris's principles spread through homesteading networks. A cabin built near Bozeman, Montana in 1889 incorporated underground flue elements combined with local stone thermal mass, adapting Harris's concepts to different soil conditions and available materials. Similar installations appeared in Wyoming's Powder River Basin and Colorado's High Country, demonstrating the broad applicability of underground heat capture principles across varying frontier conditions. Modern building science has unequivocally validated the fundamental principles that Harris pioneered through empirical observation and the integration of traditional knowledge. Contemporary earth tube heating systems, ground-coupled heat exchangers, and passive solar thermal mass applications all employ variations of the heat capture, storage, and controlled release concepts that Harris developed in his Black Hills cabin. Current building codes in cold climates now specifically address thermal mass requirements and heat recovery systems that directly descend from Harris's experimental frontier heating methods. The measured performance advantages documented during the extreme weather test established Harris's system as the first scientifically validated alternative to conventional frontier heating. Interior temperature differences of 51 degrees compared to standard construction, fuel savings of 30 to 40%, and the elimination of heating-related structural failures provided quantifiable evidence that traditional knowledge could demonstrably outperform accepted frontier practices. Harris had proven that the careful integration of indigenous thermal concepts, old-world building techniques, and rigorous empirical field testing could produce results that conventional wisdom deemed utterly impossible. By the spring of 1888, Harris's quiet innovation had transformed from a local curiosity into a recognized heating technology, spreading across the northern frontier through documentation, demonstration, and the undeniable evidence of superior performance under the most challenging climatic conditions imaginable.